Here I am. Let's see. Is there a test? Manage. Pause. No, I guess not. Interval screen. How about that? Okay. Now let's get the. I guess since there's nobody remote, I'm not going to see any little insets with people in it. Expect to see that. Let's see, let's turn it just a little bit so we get as much board as possible. All right. Let's try that on for size. Okay. Today's review for the exam next week on Chapter 12, Chemical Kinetics. Let's see. Get documents out. And pick a color that'll show up good. Start with black. Okay. Wait a minute. You were the only one here, weren't you?
For the class.
Yeah, for the class. Okay. So, have you guys had a chance to look at the material? Okay. Fortunately, we have a couple hours. Did anything come back to bite you?
I haven't had time to do it against the class.
All right.
I worked every day.
Us non-traditional students.
Okay, I'm going to skip number one because that one's not the best place to start kinetics. Best place to start kinetics, I think, is probably 8 and 9. Interpreting that reaction figure. Okay. Trouble is, the figure's not labeled, but it's given as a potential energy diagram. So it has to be like this. Energy's on that scale, and this is the reaction proceeds from left to right. Okay. So if we start here at this energy level, and this is for reactants. Might be a little. No, it's coming up okay. This is the energy level for all reactants. And then as they approach one another, maybe I should back up and give you the collision model again. Okay. What's required for the collision model? Then this will make more sense. All right. Whenever you see model, you think theory. You're trying to explain why something happens. Okay. Why reactions proceed as they do at the rate that they do. The collision model requires one, that reactants collide. And two, that a minimum energy is provided. So what does that mean? When they collide, they have to collide or there's no reaction. It's just that simple. In other words, that molecule over there and that molecule over there are not going to react because they're nowhere near each other, right? So they have to collide. They also have to collide with sufficient energy for the reaction to proceed. You have to put energy into a reaction before it will go. And that's this minimum energy that we call the, we abbreviated E sub A, which stands for activation. Okay? So they got to collide, got to have enough energy, and thirdly, they have to be oriented correctly. If, say, two molecules collide with sufficient energy, but the reaction centers, the parts of the molecules that need to react in order to break bonds and form bonds, are not oriented correctly, they won't react. In other words, if they're supposed to be head-to-head, but they collide head-to-butt, no reaction. Okay, so those are the three conditions of the collision model. Now we go back to the potential energy diagram. Okay, we have reactants at this energy level. Now we're going to pump energy into them. And that means that they have to be going fast enough. We're talking about kinetic energy. So as they approach, the potential energy of the combination increases to a certain point. Now they have enough energy to react. Yeah, I'm trying to be consistent with this picture. Now they've reacted on this side, and you have products. Okay? Now let me label it the way it is here, so it hopefully makes sense. So we've got this A. Okay? Then B is here. And C is here. And D is down to right here. So that represents a level here, from there to there. Okay. And E. So for E, we have to have an alternate potential energy pathway. And then E becomes, I have to put it over a little bit. That. Okay, I think I have everything up there. Okay. The amount of energy that has to be put into the reaction, the activation energy. Well, actually, it's kind of a giveaway because A is it. The amount of energy required is, this is E sub A. That's the activation energy. Now I'm going to add some things here that are not part of this question because we're trying to bring you up to speed. But this position here is often referred to as the activated complex. It is a combination of reactants with their added energy, and it's very unstable. So if we have just a a microjoule more than required, then it'll go over the hump and down to products. If we have just a microjoule less than required, it'll fall back down toward reactants. Okay. Now those two scenarios, either this way or that way, can happen simultaneously in the same reaction mixture. But it won't happen to the same set of reactants. In other words, if you get an A plus B for this side, then they'll yield the products. Okay? But if you have a different reactant A and B, and they don't have enough energy, they just go back to where they were. Okay? So since there are billions and billions of molecules in this mixture, you have an average value for those that have enough energy to go to products. And sometimes, let's see, I gotta stay in view here. Sometimes it's described like this. And this is the average, this is the energy distribution of all the molecules in the reaction mixture. So it'll look something like this. It'll tail off. Okay? Now, the number of molecules that have sufficient energy to go the hump and make this one will be something like this. Okay? So not all of the molecules in the mixture have enough energy to react. Okay? That's this scenario on the dark line. So you add enough energy, you get to the activated complex, and if there's just a little bit more, it'll go down like that. So what do these others mean? Well, this is just total energy from some zero baseline of the activated complex. This is the total energy of the reactants as they begin. Those are not as important as this one and that one. This one is the change in energy from that position to that position. Right? If you start with this energy and you end up with that energy, some of that energy has been stored in the product. Right? So that means it's an endothermic process. We've put energy in, but we didn't get all of it back. So think about it. What would an exothermic reaction diagram look like? It would be just the opposite. This would be high, and that would be low. Then you would put in a certain amount of energy, and you get a lot more back than you put in. That would be exothermic. Okay?
So an exothermic reaction, you put a lot more energy in, you'll get back on the other side.
No, endothermic.
Oh, endothermic.
Right, you put more energy in, but you don't get all of it back. Right. So actually, if we started over here with what we're calling products and ran the reaction backwards, that would be exothermic. So an endothermic reaction in reverse is exothermic.
We lost heat somewhere. Lost energy.
Going this way?
Yeah.
Right, right. You get energy out more than you put in. See, the activation energy from going this direction is what?
Yeah, from that line up.
It goes from here to here.
So the top pump there is the potential. So what's the dotted line pump then?
Oh, okay.
The actual?
No.
No?
Mm-mm. catalyst. If you add a catalyst to your reaction mixture, and we have to define what a catalyst is, right? A catalyst participates in the reaction, but not consumed. So a catalyst enters the reaction on one side and is reconstituted on the other side. Catalytic converter in your car.
It's been a while since I've had shop.
Platinum, palladium.
I'm kidding, I've never had shop.
Usually platinum and palladium are coated on ceramic beads, and they're just packed in your catalytic converter. And the oxides of nitrogen, I'm going to have to erase some of this because there's not enough room on the screen. Here it is. So you get your, for instance, you get oxides of nitrogen that are formed in the combustion process. Well, those are bad. They create smog. So what you want to do is, I'm not sure how the reaction goes, but you end up with, and maybe some oxygen or something like that. I don't know. But you don't want these. So this proceeds at a certain rate without the catalyst. With the catalyst, it may not proceed fast enough at all, actually. But with a catalyst, it proceeds to these products at an extremely rapid rate. And the catalyst is platinum and palladium on your ceramic beads, coating on the ceramic. And these interact with the platinum and palladium, and in the process promotes this reaction, but they're not consumed. They're still right there.
They just somehow act to change the bonding.
Yes, yes. They promote the breaking of these bonds and the forming of bonds that give you that and possibly that. That's one type of catalyst. I'll come back to that topic in a few minutes. This explains what happens when a catalyst is introduced. It doesn't change the products that are produced. It just gives the reaction an alternate pathway. And in the process, it reduces the energy required for, okay, so in that case, this E sub A, this E is, E is the activation energy for catalyst. It takes less energy to get to an activated complex state and produce products. So what it actually does is, since there's less energy required for the reaction to proceed, with a catalyst, you get more of the molecules reacting to produce products than you would without a catalyst. So with this diagram, we're showing that we have more molecules. It's the same energy, same temperature for the reaction mixture, but more of them can react to produce products if you have a catalyst. Let's see. I want to get this right, so rather than rely on my memory. In your text, you'll find an equation called called the Arrhenius equation. And Arrhenius said actually, I'm getting ahead of myself. Let's hold on that for just a minute. Because with this introduction, now we need to talk about how do we express reaction rates. This determines how fast a reaction will go, right? The more of these molecules that you have with sufficient energy, energy and orientation to produce a reaction. The more of them you have, the faster the reaction goes, right? Because you're producing more product with the same amount of energy. Right? So how do we express that reaction rate? Okay. The simplest way to express the rate, let me get rid of this because we're not talking about Arrhenius right now, is the rate of reaction is equal to a change in the concentration of either reactant or product, right, over a given period of time. So that's the basic expression for reaction rate. Typically what we do is we look at the disappearance of a reactant. And the reason for that is if we have a reactant here that produces some product, we know that as we get more and more and more of the B, then the competing reverse reaction becomes significant, right? So we want to watch the disappearance of A at the very beginning, where there's so little B that the return reaction does not influence the forward, right? We're going to look at the balance of these two in the next chapter. But for right now, to determine the reaction rate, we typically look at this one and its disappearance, right? So this change here is going to be a negative value. Okay, so how do we express the reaction rate? Let's see. In terms of a rate law, okay? So the example that's given in, and I assume this is taken straight out of your text, so the example that's given is for this reaction, this is a gas, producing gases. And typically, this concentration is either in molarity, or if it's in as a gas, it can be given as partial pressure. So the partial pressure of NO2 will be just as effective. But we're gonna try to stick to molarity, just so that we don't complicate things. The rate law for this reaction will then be some constant times the concentration of NO2 to some power. Okay? Now, first lesson is that value right there has nothing to do with any of these coefficients. This is called the order of the reaction. The order of the reaction is experimentally determined. Right? So that's what we're going to do today in lab.
The whole point of the lab figuring out which order it is, 0, 1, 2.
What's the order? Well, yeah, that's the first point. Second point is, what's this value? The rate constant. Okay. The rate constant depends entirely on, well, the reaction, of course, but also on the temperature. So you have to conduct the experiment at a given temperature. You change the temperature, you'll change the constant. Right? And that just makes sense because of that earlier diagram. If you change the temperature, then you've changed the number of molecules that have sufficient kinetic energy to react. Right? So the reaction rate is intimately tied to the temperature. And that's where Rainiest comes in, but I don't talk about him right now. Okay, now the simplest reactions to study are those where you only have one reactant, right? So in this case, you may or may not require a collision. When we start talking about collisions with unimolecular reactions, what we're talking about is collisions between that and some other NO2 and NO2. That's possible. And then we're getting into mechanisms. You know, what are the elementary steps? Because this is the overall reaction. But usually that overall reaction can be broken down into individual elementary steps. Okay, so hold that thought for a second. And the, let's see. Okay, I mentioned initial rates. We typically determine these values at the very beginning of the reaction. Okay. Now, that doesn't mean we can't let the reaction proceed, but in order to minimize the reverse reactions, we want to look at the reaction at the very beginning. So what are the possibilities here? Well, the first lesson about reaction orders is they don't have to be whole numbers when you determine them experimentally. We try to use whole numbers because it's just easier to deal with. But a fractional n is not forbidden. But for simplicity, we're going to discuss whole number reaction orders and how to detect them. Okay? So, first possibility. First possibility is where n equals 0. 0 order. 0 order reaction. Okay? And we're gonna define these in terms of a single reactant, A. So if we have a reaction where A produces a product, then the rate expression for 0 order is K times A to the 0, which is equal to K. Right? So for a 0 order reaction, the rate is equal to the constant. Doesn't matter what the concentration of A is. And some reactions are like that. This is known as the differential rate expression. And that's derived from calculus. So you don't have to worry about that. But often the integrated version is more useful. And the integrated version of this is, if you know the final concentration of A is equal to minus K times the time, plus the initial concentration of A. See how that's more useful, because if you know where you started from, what the K value is, how long it took you to get there, then you can calculate what the final concentration is.
I'm still a little lost on what exactly the reaction order number, what does that number really mean exactly?
At this point, there's no intuition that can help you with that. It's just experimentally determined. Okay. Now, when we get to elementary steps, the reaction order does have a correlation with a term called molecularity. That is, how many molecules are involved in the reaction.
Next chapter,
Huh?
right? The next chapter, right?
No, it should be in this one. Because molecularity is part of the discussion of kinetics.
So it's not really tied to the concentration amount?
Oh, that value right there?
Yeah.
No. No, in fact, if we have a zero order reaction, then it doesn't matter what the concentration is in the differential expression. Right? But it does have value. Once we determine what K is, then we can use, or actually we can use this expression to determine what K is. Okay, let's get all our orders up there, and then we'll talk about, well, as we go, we'll talk about how to do deduce the order from your data, because that will be useful for today's exercise. Okay, so this is the rate expression, and notice that if you plot A against T, then the slope is a negative K, right? Y equals mx plus B. Right? So this one is going to be, let's see, I need a little bit of room down here. This one is going to be like this, with time, and then concentration of A. Okay? So this one is going to, you just plot the raw data, and you get a negative slope, which is equal to K. Okay? So if you were to plot the data that you determine, just the raw data, and you get a straight line with a negative slope, you have a zero order reaction. The other bit of information that's useful is the concept of half-life. So have you ever been introduced to the concept half-life? How long does it take for half of this reactant to disappear? That's the half-life.
Yeah, like kind of long drugs.
Yeah, right? Or radioactive decay. Lots of sciences use the concept of half-life. So for this reaction, for zero order, the half-life is equal to whatever the initial concentration is, divided by 2 times K. Right? And this half-life, this A value here, doesn't actually have to be at time 0 in your data set. It can be any position you choose. Then you say, how long does it take to go from that place to half its value? Okay? Now, first order. Okay, for first order, the rate, you can probably guess, is A to the first power. Right? I didn't write 1 in there because it's stupid. It's redundant. We don't write 1 if there's already a symbol there. Now, that's the differential expression. And the integrated expression is the natural log of A is equal to minus K times time plus the natural log of A0.
The initial.
Huh?
The initial.
Yes, the initial concentration. So here's Y equals mx plus B. So if we plot this one, and we need the natural log of A, concentration, versus time, and then that will be a negative slope with K.
Yes.
Right.
But it's log A instead.
Actually, this is negative K. Right, natural log.
Is that a function on the calculator and then,
Yes.
because I don't know.
Yeah, oh yeah, it's there. Let's see, where's the log? The common, there's the common log. Natural log is right below it. Whereas 10 to the x is the anti-log, e to the x is the anti-log for natural. Okay, I need to go back. Okay, now this one has a half-life expression as well, which is 0.693 divided by K. Notice that the half-life does not depend on the concentration of A. So no matter where you look in your data set as your starting point, the half-life is only dependent upon the K value. Doesn't depend on where you start. So the half-life is going to be the same no matter where you start. Whereas for the zero order, the half-life is dependent upon where you start in your data set. So the half-life will change depending on your starting point. Whereas first order, half-life doesn't matter. Anywhere you start in there, it's going to be the same value, half-life.
The same value?
Yep, the same half-life, no matter where you start in your data set. So if you have your values here and the time, and you start here, and you go down to half the concentration, it's going to be a certain time period. If you start here and go down to half its value, it's going to be the same time period. Okay. Second order. Oops. Be consistent. It's like that joke. I have 3 points. Number 1, they give you number 1. And B, they give you the next one. And then lastly, anyway, so second order, the rate, the differential rate expression is still K times A to the second power. The integrated rate expression is not the log, but the inverse. Okay? So if we plot the inverse of A against time, like time is on the x-axis, then the inverse of A plotted against time will give you a straight line, but notice it's positive. So it'll be this direction with a slope of K. Okay. half-life expression is 1 over K times A. So if you take your data and you set it up, let me move this over. Yeah, that's better. So if you take your data and you say you have time here, right? Just whatever time intervals you have, 1 minute, 1 second, doesn't matter. Some reactions happen so fast that you have to plot their progress using lasers. It's so fast. Some of them are slow. You know, so it might take an hour to lose half of the reactant. Or they might, and in our case, it's a matter of minutes. So it's something we can do in a lab setting, in a single lab class. So you're going to get your data at these time intervals. You're going to get a concentration of A, right? Values there. So you take these values and you convert, right? So you get the log values there. And then you take those values again and you take the inverse.
And you plot that and see which one's safe.
Right. Then you plot those, each one against time, and see which one's a straight line. Okay?
So if you plot a zero order thing, trying to use the log of it, it won't make a straight line.
No, that's right. Only one of them will make a straight line. Of course, there are practicalities involved. And if during your reaction, particularly for the one we're going to do today, we'll watch the disappearance of color from our dye as the bleach affects it. Eventually, you're going to get down to where it just tails out. That tail, if you incorporate all of that tail into your data set, it will skew your data so bad that none of them will be straight. So you have to draw the line somewhere. And the best way to do that is just take all your data, plot it, make your conversions, and then use Excel is the best way. Use Excel to draw a graph of each one. And usually, once you've got those graphs drawn for each one, I think I gave you examples, didn't I, in your handout? Not that one, I'm sorry.
Oh, a bunch of pages after. This is the biggest laugh I've ever seen.
If not there, then it is on Blackboard. Show you examples.
Addendum from the structure source.
Yeah.
It's like 8 pages.
Does that have a plot? What may happen is you'll get a plot of one, and it might go like this, and then kind of do like that at the bottom. Then you know, chop it off there. That's the straight part of your line. The others, you won't be able to do it with the other two. So it's not like we're cheating. But that's how you determine the order. Once you have the order, then you can pick which one is correct and solve for K. And this is the best way to solve for K. Use your integrated rate law, but you have to determine which one to use first. Then once you determine which one to use, you can plug in a value starting point, ending point, how long did it take to get there, solve for K. Okay. And once you have K, you can do a number of things with it. You write the rate law, of course. You can find out what the half-life is. Sometimes you can use the half-life to find out what K is. If you know which one of these it is, then you can find out the half-life of your reactant. plug it in here, and determine what K is. In this case, of course, you need to know the initial. Here you need to know the initial.
How is the initial determined? Is it like measured in grams? Like one we're using bleach at like grams? Sure. How's that?
Initially, what we're going to do with bleach is we're going to determine so many drops for full strength and so many drops then for half strength. Those, we're going to do 2 reactions there. But one of the pre-lab questions was determine what the concentration of bleach is in molarity. Right? Because you need to know the molarity, and you also need to know
grams per liter.
The mass. There's so many drops of bleach you're going to be adding to your little cuvettes. So you need to know what's the mass of those drops, or what's the volume of those drops. It's easier to do mass. So you do so many drops and you weigh it. You might do so many more drops at a different, and weigh it to be sure, just check yourself. But if you know the mass and you know the density, which the density is given, then you can calculate the volume. And you know the volume of your bleach that's being added to the solution, then you can calculate based upon 6%, which is mass volume, 6% sodium hypochlorite. You can determine what the molarity is based upon the final volume of your reaction mixture. So you got to keep track of a lot of details. Yeah. Yeah.
So, when you write that subscript after the A brackets?
This one?
Yeah, on any of them. What is that referring to? The grid?
The initial.
Initial.
Wait a minute. Did I put it in the wrong place? I did put it in the wrong place. One of them's in the wrong place. Let me see which one it is. It's this one. No, it's not. No. This is a different 0 than that. This is the order. This means initial. Beginning. At time 0. Okay. I was
just trying to make sure I understood.
Right.
And the only time that the time so in the 0 order, it matters when the time. Which time? Or you're just saying that's the value at 0 at the 0 time for the half-life?
Oh, half-life. Yeah. The starting position does matter for half-life.
But we could choose a different point. Say, and how would you?
Yes.
How would you write that? Like, how would you notate? Like, if you chose a different time for A. Like, what? Just what that look like?
You could annotate it as put the actual time here as your starting point. Right? If you started at 4 seconds rather than at 0 seconds. Or
so the A is an expression of either molarity or partial pressure, you said?
Yes.
And so like for today's work, we'll be calculating molarity.
Molarity, yeah. And it's simpler that way. Just
so the concentration is just molarity.
Yep. Right. The kinetics can be extremely complicated. Right? You probably figured that out already. So what we're trying to do is simplify it so we can gain a basic understanding of kinetics so that we can use that information to have a better understanding of equilibrium. That's why kinetics comes first, because equilibrium is actually a competition between kinetics that way and kinetics this way in a reaction.
Is equilibrium that point at which it's not going either way?
Right. The forward rate, the reverse rate are balanced. That's equilibrium. Right. So you're getting a preview of the next chapter. Okay. So now that we let's see, now that we know what order we're dealing with.
Is it just 0 first and second, and that's it?
Yeah, actually, right. So you're going to use that information to determine what's the order of your, one second. What's the order with respect to the concentration of dye?
Can you give a quick math lesson, because I haven't had math since high school, the log function? Like, what does that represent exactly?
This right here?
Is that a number, like, so pi is obviously a number, I get that, but I don't know what log is. Is log a number?
Yeah, it's a transformation of one number into another using the function of the log. They're related, yes. Right. So first, let's do the definition. Let's use a more familiar version, common logs, right? So if we have a number, say,
5.
I'm going to call it B because I'm thinking ahead. Let's say B to the X is equal to some value. The log transformation says that no, that's not right. Okay. The log transformation says that the log of A is the power of B. This is the base. So that just means if you have the log of A, say, let's keep it simple, example. So the common log is base 10, right? So if we have 100, so what power of 10 will give you 100? 2. 10 to the what power?
The exponent.
Yes.
Oh, right. Oh, okay. So 10 to the second.
10 to the second power is 100. So B to the X power is A.
Common laws are usually B is what you think.
Yes, that's why I chose B.
Okay.
So now if we write this for natural log, it just changes what the base is. It doesn't change the
Call that one common?
this is the common log, base 10. This is the natural log. It's base E. Yeah. So the base there is some value here. So that means that E to the X value is equal to A. So what power of E gives you A? Right. Now E is it's been around for probably a couple hundred years. It's mathematical, whatever. I don't know enough to explain where it came from, except that it's roughly equal to something like 2.303, something like that.
E actually has value.
Oh yeah, has value.
Oh, wait.
Fantastic.
So,
Maybe not even that, because it's not. It's supposed to be a, what do they call it? Pi, irrational number.
yeah,
It never repeats.
right.
Right.
Same for this number?
The same for E.
So
Yeah.
you're saying the natural log is an irrational number, like pi?
Yep.
It has a value.
Right. It has a definite value, and it just depends on how far out you take it.
But it is, so the natural log, how do you read that again, that sentence, that sentence?
This one?
Yes.
Okay.
Read that.
The natural log of A is the power of E that equals A. E to the x power is equal to A. So the natural log of A is actually the power of E.
So basically, its application is to get rid of exponents of the problem where it makes sense.
Yeah, the rules governing operations for logs are much simpler and easier to deal with. Right, so if you have, let's see, what would be an example?
I just remember you had something like a to the 3 plus 5x power, you did log of that and got rid of a, and it just put 3 plus x.
Oh yeah, say we do have an expression, and Arrhenius is a good example, to the 2x plus t, something like that, is equal to some value. Okay. If we take the natural log of that, the natural log, there e to the 2x plus t, is equal to 2x plus t. Let's look at it over here like this. So what if this were that? Like that. 10 is the base. So the natural log, the common log of 10 to the 2 is actually the power of 10. So the natural log has e here and e here, then it's just equal to that value, just like this one is equal to that value. Okay? The other thing that's good about logs is if you multiply two numbers, say if you have A times B equals some value. Well, if A and B are extremely complex numbers, it might be useful to just take the log of that expression. So the log of A plus the log of B is something. Right? Rather than having to multiply those two numbers, you just take the logs and then add them together. Then you get a value over here. Then to find out what the answer up here is, you have to take the anti-log of this value. No. No, the anti-log is 10 to the x. So you would take 10 to the c equals your answer.
I'm going to assume that C is not going to be some outlandish as well as number.
Doesn't matter. You got a calculator. You just plug in C and hit 10 to the x. You get an answer.
So, just because, thank you for humoring my lack of math knowledge here, but so back to like our first order calculations, if I have the values for A, I mean, how do I just don't know, how would I input the numbers to get how do I do that? Can you,
Oh, on your calculator?
yeah, like if I, am I more than likely solving, am I solving for K or am I solving for A? Or I just need an example to
Okay,
see how.
let's do an example.
Yeah.
Let's look at a data set here and see if we can figure it out.
I don't remember having logs in algebra 2 in high school. Maybe you did.
Okay.
It's been a while.
Number 2. This gives us an opportunity to look into the method of initial rates at the same time. Oops, that's not it. Here it is. Well, that one's a little, that's more complicated than that. Hold on a second. Huh?
Those were the easy questions.
Well, yeah. Well, might as well do it. Method of initial rates. So I'm gonna have to erase this to make room. So in the method of initial rates, you actually have several experiments that have been run. Actually, initial rates skips the step where you actually determine the rate. All right, let's do this. I'm gonna put the data up here, and then we're gonna talk about it. You have to have a balanced equation. I think that's oxalic acid there. That's the manganate ion. So from last semester, you realize, of course, this is a net equation, right? Because you got 6 hydrogens and only 2 manganates, so that can't be part of it. There must be a counter cation in here for it that we just, it's a spectator, right? This is the only important parts of the equation. And this produces 2 plus CO2 and 8 water. Okay. So I'm going to use this equation. This is my header. So for this one, we choose concentrations. And these are all molar. We choose concentrations so that and of course, we're looking at the disappearance of reactants, so it doesn't matter what those are, because this is initial rates. We want to know what happens at the very beginning when there's practically none of that being produced. Okay, for the same reason as before. We don't want competing reverse reaction. So this is one experiment. And then for that experiment, we determined that the rate is 2 times 10 to the minus 4 molarity per second. And then the last experiment, so we have 4 experiments here actually going on that we've conducted to get this data.
And you said you were just choosing different concentrations?
Yes, but with a method. There's a method to this madness. What you want to do is compare 2 different experiments such that, see, we have that reactant, that reactant, that reactant. How do you know which one's changing when, right? So since it's initial rates, we start off with 2 of the reactants that are held constant from one experiment to the next.
Right.
So this one, we hold that one constant and that one constant. This is the one that we let vary. Okay. Then once we determine what that one is, we hold this one constant and that one constant. Then this one varies. Okay. Then we hold this one constant and that one constant and that one varies. Then we get a handle on each one. Okay, so how do we do that? Well, we do ratios. First of all, let's write the rate expression for this experiment. For that equation. We'll use the differential version. There's a K for this reaction. And then for each of the components, we have an order. 204. Okay. So we want
you call this rate expression?
Yeah. This is the rate law. Right. The rate law for that reaction. We have an order from the manganate ion, we have an order for the oxalate, and we have an order for the protons. Right? So each one of these has its own order, and this could be 0 order, that could be 1, and that could be 2. Each one has its own order. And then the overall order, which I left out for the discussion earlier, the overall order is just N plus M plus P. Just add them together. Okay.
So in question number 2, there's just...
That's just a setup for the problem. Now we need to do the solution for the problem. Okay, using that information. Let me turn that over just a little bit. Okay, let's identify these. This is number 1, 2, 3, and number 4. So for N, for determining the value of N, we need to hold these two constant and let this one vary, because that's how we get this one.
Varying concentration and the initial concentration?
Yes, we only let this one vary. We don't let those vary. So if we write, then we ratio experiment 1, experiment 2. Actually, we're going to ratio 2 over 1 because this one's larger than that one. We want whole numbers, not fractions. Sure. So if we say experiment 2 divided by experiment 1, we have this rate expression here. This rate for 2 divided by this rate for 1. Rate 2 divided by rate 1, right? And then if you expand that value, rate 2 is actually 8 times 10 to the minus 4 divided by 2 times 10 to the minus 4. Right? This one divided by that one. And that is equal to the other expressions. So for the manganate, which is the one we're after, for 2, it's 2 times 10 to the minus 3 to the n power. And for the first one, it's 1 times 10 to the minus 3 to the n power. Now, what are the others? They're the same, right? Because we held them constant. Right? Well, I'll fill this one in to begin with. 1 times 10 to the minus 3, and 1 times 10 to the minus 3, and this one is 1 and 1. Right? So when we start resolving that expression, that ratio, That one cancels that one cancels that one, and all we have left is this divided by this equals that divided by that. Okay? Yeah, I mean, we're just ratioing. We're taking this expression and ratioing experiment 2 for that divided by experiment 1 for that. So now we get, what's this one? 4, right? Right, 2 into 8 is 4. What's this one? Well, we can reduce that expression to 2 times 10 to the minus 3 divided by 1 times 10 to the minus 3 to the n power, right? That's a valid mathematical manipulation. Okay? Okay.
So it's 2.
So this is 2 to the n power equals 4, so n equals 2. 2 squared equals 4. So now we know that for this one, that one equals 2.
Now we do the same thing again, 3 divided by 2.
We do, yes, we'll do this one divided by that one for m. So we do experiment 3 divided by experiment 2 equals rate 3 divided by rate 2. So rate for 3 is 1.6 times 10 to the minus 3. And rate 2 is 8 times 10 to the minus 4. And
So this is called the method of initial rates.
right. Now you're probably wondering, where do we get that rate? Well, since it's initial rate, all you need is the starting concentration and the next smallest interval you can get concentration. That's it. So this expression is going to put this one divided by this one, and that's to the n power. And then this one, which is going to be, let's see, 3. No, here. 2 divided by 1. 10 to the minus 3 divided by 1 times 10 to the minus 3. And this one is to the m power. And then the hydrogen is to the p. And since we held those constant, they cancel out. So now we have 2 divided by 1 to the m power. Which is equal to what? This one? So let's change this one, since we can't divide those together. Change this one to minus 4, right? If we change that one to minus 4, it makes this 16. Are we good? Okay. So that means this is equal to 8 into 16 is 2. And 2 equals 2 to the m power, m equals 1. So now we've got m equals 1. Then if we do the same thing, where we let this one vary, so that's this one, and so 4 divided by 3. If we do that one, we end up with p equals 0. I'm trying to conserve time here.
So those are
orders of
orders.
individual reactants. So the total,
So that one is a second, that one's a first, and that one's a zero.
yes. So what's the overall order for this reaction? 2 plus 1 plus 0, 3. Overall reaction for this, overall order for the reaction is 3.
You just add them together.
Mm-hmm.
So, back to question number 2, which of the following is the correct rate law? So then we'll.
Oh, okay, so,
Write down.
right, we didn't determine what K was. Right, so we're leading that to a different, that wasn't part of the question. So we look at D and see that it has the correct order. And since the protons are 0 order, that term drops out.
Why?
Because anything to 0 is 1. Okay? You don't write it in. Because if this is 0 order, it just becomes 1. So the rate is K times this one, times 1, and we never write 1 anyway. That's why the law is that, and not H to the 0 order. Well, that's not a choice anyway. So I was kind to you there. I didn't throw you a curve and put protons to the 0 order. That's one we didn't get to last week. That whole method. Okay. 3 gives you a way to use information that we've determined from here. Not in this particular reaction, but in a comparable reaction. What do you do with those values? What does it tell you about the reaction? Okay, so let's remove this and go to 3. It won't take long to do that one. Actually, what we've shown here is an alternate way to find out what the order is, right? Before, we talked about actually running the entire reaction, plotting the data, and finding the order. That's a valid way to do it. But if you have this set of reaction rate experiments and choose your concentrations correctly so that you can compare changes in only one at a time, then you can use the method of initial rates to do the same thing that we did in that first discussion of 0, first, second order. It's an alternate way. Okay, so when we get to 3, the question is, the rate expression for a particular reaction is this. So we have a rate constant, concentration of A to the first power, concentration of B to the second power. So if the initial concentration of B is increased, so if B goes from 0.1 molar to 0.3 molar, what happens to the rate? So how much did the rate increase? I mean, how much did the concentration increase? 3 times, right? So we increased it 3 times, and we're going to square it. So what happens to the rate? 3 squared is what? 9. So the rate increases 9 times.
So the higher the concentration, the rate.
Yes. Do you see that? Yeah. We increased the concentration that much. What if we did the same thing for A? Just 3 times for A, and let this one constant. What would happen to the rate? 3 to the first power means that the rate would increase 3 times, because it's only to the first power. What if, okay, let's go sublime to ridiculous. What if we let both of them increase that much? Right? So this one's going to increase 3 times, and this one's going to increase 3 times. Okay? So that means this one would go 9 times, this one would go 3 times, so 3 times 9 is 27. So the reaction, if we let both of them go up that much, then the combined effect would be 27 times increase in the reaction rate. That's one of the uses of orders. I can tell you what to expect when you change the concentration.
If the reaction rate doesn't change at all, it's 0.
Oh yeah, right. If this was 0 here and that was 0, then those terms would go out and the rate would just be constant. Right? It doesn't matter what you do to these concentrations if they're both zeros. Yeah.
And again, in that expression, K times A times B squared, that 2, I mean, that's the order.
That's the rate law, and it gives you the individual orders of the reactants. A is first order, B is second order.
That you treat it like an exponent.
Yes. Yes, when you write, we put that change from from point 1 to point 3, that's a 3 times increase. And the exponent effect of the order is, in the B case, is 9 times because it's 3 squared. Okay. Okay. Perhaps we should discuss the concept of elementary steps. Let's see. Oh, here we go. In a reaction mechanism, what we're saying is, let me write this. So, have a reaction mechanism. We're taking the overall reaction and breaking it into individual steps, these elementary reactions. And to have an elementary reaction, in an elementary reaction, there are no intermediates. In other words, that's actually what happens. Right? That's why we call it elementary. You can't get any simpler. So, for instance, let's see. The example that's given in the text is this one. So NO2, they're all gases, so I'm going to leave that out. Plus carbon monoxide yields nitric oxide plus carbon dioxide. That's the overall. In the mechanism, and it occurs in steps. In the mechanism, they're saying that NO2 plus another NO2 yields NO3 plus NO. Elementary step. So you get two of these smashing into each other, and the product is NO3 and NO. It's an elementary step. Then in the second step, you get this NO3 then reacts with the CO, and it produces an NO2 plus a CO2. Okay, so they're proposing a two-step reaction here. So the first rule, well, actually, let me back up. When these steps are proposed, you can propose mechanisms for a reaction that have 20, 30, 40 steps. I mean, kind of ridiculous, but that's possible. And the method of proposing mechanisms for a reaction, I assume that those chemists that are involved in this type of stuff have some intuition about it. But technically speaking, you could propose just any number of steps for a reaction. Then what you have to do is take all of those proposed mechanisms and use what you know about the reaction rates to eliminate the ones that make no sense. Okay, it's a process of elimination. And you pare it down to the final 2 or 3, and then you might have to run another experiment to eliminate those possibilities, but it's an empirical process trying to figure out the mechanism. And I know what's going through your head. Why bother? You know, what does the mechanism tell you? Right? Hopefully we'll get to that in a second. So the first rule that validates a mechanism is you have to be able to add the steps of the mechanism and get the overall equation. It's kind of like Hess's law, right? You can break a, if you want to determine the enthalpy of a reaction, you can have multiple steps in there, but they all have to add up to the overall in order for it to be valid. Same concept here. These have to add up to give you that one, right? So here we have NO2, that's good, but we got another NO2. Well, there's an NO2 over here, so those two cancel. And then there's an NO3 over here, but there's one over here, so they cancel, right, on either side of the arrow. So now what do we have left? We have NO2, and then we have CO, and then we have NO, and then we have CO2. So that's a valid mechanism for that first condition. Next, what you're looking at is, and it's not given as an example in the PowerPoints or your textbook probably, but I'm going to make a point of it here. Let's just suppose that we know from other experiments that this one is fast and this one is slow. Those reaction rates. Don't ask me how I know, right? But we have to bring in other experiments to tell us that. But if we know that, that means this one is the rate controlling step. It doesn't matter how fast this one is. This is the bottleneck. That determines the overall rate. Now, if we determine the overall rate for the experiment, right, we do the rate law. and we know something about this slow rate, and it's equal to that rate, then we're on the track. Right? If this rate is equal to the experimentally determined rate here, then we know that we have possibly a valid mechanism. Right? If these rates, the rate of this one and the rate of that one, do not agree, then this probably is not a valid mechanism, because the overall rate is determined by the bottleneck. Okay? Now, something about in elementary steps, if you have if an elementary step has only one molecule as a reactant, then you have a unimolecular. This is elementary step. Unimolecular just means one reactant. If you have two, like this one, this is a bimolecular. These are the most common, unimolecular, bimolecular. This one, termolecular, has three. So this is one, this is two, this is three reactants colliding at the same time. We'll go back to the collision model, right? For this one, it doesn't have to collide. It just decomposes or does something. But the bimolecular, they have to collide, and it's not too difficult to envision the collision of two molecules coming together with the amount of energy they need and the proper orientation. But the termolecular requires that three molecules come together with sufficient energy and oriented correctly, all three of them. That's why this one is extremely rare. And for chemists to resort to a termolecular step as an elementary, they have to eliminate every other possibility before they'll go to this one. We have to force this one on them, in other words, because it is so rare. I mean, just the probability of not having a termolecular is astronomical. Okay. Okay, we've talked about the collision model. We've talked about our another term for activated complex is a transition state. You may see it both ways.
Where's that?
It's on page 8 of your PowerPoints. Middle of the page, left-hand side. And the next one. Transition state. I called it activated complex, which is valid, but your authors refer to it as a transition state.
There's just a picture of a yellow box here.
Yes. Because that's that was an embedded animation. But the one to the right of it looks more like what I drew on the board initially.
Okay, so say it again, you said what?
Activated complex and transition state are synonymous.
Activated complex?
Activated complex, yes,
Yeah.
is equal to transition state.
That's just for one reaction. That happens like hundreds and hundreds of times, right?
Oh yeah, yeah. Oh yeah. Right. That's just for one set of reactants on the microscopic scale. Let's see. Okay. Oh, technically speaking, if you have an elementary step where there's only one, if it's unimolecular, then the overall effect on the reaction is first order. If you have two in an elementary step, then the effect is second order. If you have three, then it's third order, and we didn't talk about that one.
So are we going to be needing to do the elementary steps to determine what order of it is, or are we just going to do it as a whole? We're not really worried about elementary steps, more like the entire reaction as a whole.
Yeah, that's more important. The elementary step discussion is just to clarify what value is actually experimentally determined the rate. The experimentally determined rate is useful in deducing which mechanism is probably the best. Because the slow step in your elementary steps is the rate determining step, and it should be equal to the experimentally determined rate. The slow step should be equal to your experimentally determined rate.
That the experimentally determined rate would be like the slow rate plus the fast rate, so they don't have to happen. Or do they happen at the same time?
Yeah, they can. But the slow step in the mechanism is the bottleneck. In other words, it doesn't matter how much. If you have a fast one, let's do this one. Say you have a fast step, 2, 3, and a slow and a fast. Right? This one's going to produce product very fast. At least one of those products is then used in the slow step. Doesn't have to be all of them, but just one of them.
For the entire reaction.
Right. So whatever's produced over here then enters this slow step, and it produces product. And then something from this product may interact with something from up here, but then it produces the final product, or products. Okay? So this one proceeds very fast, but it's stuck out here. It can't do anything because this is the bottleneck. Nothing's going to happen until this one gets finished doing its job. Right? So once this is produced, then the next fast step can go and make the final product. But this one determines the overall rate because it's the slowest one. It's the weak link in the chain. I don't know how to say it any better.
I understood what you just said, but I guess, I mean, you were just saying, like, why wouldn't you add them all up together?
Yeah, I'm imagining like a timeline. Even if the fast one's really fast, it still took a second. And then the slow one, you know, it might take like 30 seconds. But I don't understand why you still wouldn't add that 1 second. Because it takes that much time for the entire reaction to complete.
Okay. That fast elementary step is building up product. Where are they going to go? I mean, if the slow step never happens, they just sit there. Nothing happens. So there's no influence of that fast step on the overall rate.
Oh.
For instance, in biochemical terms, if you had 3 steps, and you can do this in biochemistry as well as pure chemistry, inorganic. If you have, and these are enzyme-mediated reactions, if you have a fast step, slow step, fast step, then all you have to do, or if you have even if you have 3 fast steps, one of them is going to be slower. But all you have to do is introduce an inhibitor to your enzyme or a poison, and it just completely shuts that enzyme down. You produce product up here, and that's it. That's as far as it goes. It won't go any farther. So the reaction rate, the effective rate is 0. You're not getting any product, right? You're getting the intermediate step, and that can be detected, but you're not getting any product for the overall reaction. Okay? That's why the fast steps are not added in. Everything depends on the bottleneck. And in fact, some herbicides do exactly that. Let's see, what do they call it? Not Roundup. We used to call it Power Quad. Now they call it Gramoxone. It's a contact herbicide. Spray it on the plants, and it just kills the tops, doesn't kill the roots. Not like glyphosate, which is Roundup. Roundup goes to the roots and kills the whole plant by a different mechanism. But this one, Gramoxone, was developed to control vegetation on slopes that were too steep to mow. But you don't want to kill the roots, because if you kill the roots, then there's nothing holding the slope, and the next big rain comes along and the whole thing just slides off. So you want to control the tops. So they created this chemical, or found this chemical, that would inhibit, or actually short circuit, the one step in the cytochrome chain, which is energy producing. And what it does is, the fast steps up here, they just keep going. And what happens there, they produce their own little products, but in the process, they produce massive amounts of heat, energy released, which is not being used in the next steps. So all that heat builds up, and it just cooks the cells. So that's a practical example of understanding kinetics, mechanism kinetics. You don't want to get any of that stuff on your toenails, they say, because your toenail will drop off. So it's not just for plants only. So you always, if you use Gramoxone, you want to wear impermeable boots. Rubber boots are best. You're going to be spraying a lot of it. Oh, I guess y'all need to take a break. Okay. Let me see how we're doing on time. Got another half hour.
I'm assuming we're going to discuss the lab before we go jump right in, right?
Yeah. If we can, if I've covered most of the topics, that's what I want to be sure and do. I think I have. Okay. Last topic before we move to discussion of the lab today, so you know what to expect, is the Arrhenius equation.
Not to be confused with erroneous.
Right. For some people, it may be
Sorry,
erroneous.
that's the best joke I got for today so far.
And it's recorded. Okay. The Arrhenius equation, and this version of it gives you some information, but it's not the most useful version. That K is the rate constant. Okay, we determined that by other means. That is some arbitrary proportionality constant. There's your E, just like in the natural log, base E. And then the power of that E is the minus A sub E, which is activation energy for the reaction, divided by R, and T is temperature in Kelvin. Okay. R is the universal gas constant, the one that uses joules for energy. It's like 8 point something.
8.3145.
Yes. So Arrhenius said that this K value is related to the temperature and the activation energy. And if you change the temperature for a given reaction, you change the K. Okay? If you change the activation energy, you also change the K. And the activation energy can be changed using a catalyst. Okay? As long as you don't use a catalyst and just vary the T, then you can gain some insight as to this, what this is. So if you determine the K for that temperature and then the K for a different temperature, you can use those two simultaneous equations to calculate what the activation energy is.
Is this all regardless of order?
Right, right. This is the K from the rate law. But that's not the most useful form. See, this is the analogous to the differential equation for the rate law. Now, the integrated form is much more useful. Okay, natural log of your K is equal to minus E sub A divided by R, right here. Inverse of T and log of A.
That coffee.
I don't know if that's what we want. It's just black.
So how do we get this one? All you have to do is take the natural log of that equation. Right, natural log of this, and the natural log of this is, remember the natural log of A times the natural log of B is the natural log of A plus the natural log of B. So the natural, wait a minute, yeah. So this would be the natural log of this term, and this would be the natural log of that term, okay, based on log functions.
So you have the more useful version of Rainiest's equation.
Is this one?
The applicable one. We
Yes.
can't really use the top one. We can use that one now.
Oh, yeah. Yeah, you can use this one. This is still valuable. In fact, one solution that I gave you on page 9 at the bottom here actually uses this one. Remember when I did the ratio thing? Yeah. But the value of this one is, look what it looks like. It's a straight line. If you plot the log of K against 1 over the temperature, the slope is going to be negative E sub A divided by R. And the intercept is going to be the log of A. So if we plot 1 over T and against log of your K values at different temperatures, remember that the K is going to change with temperature. So if we take, and we really only need 2. If it's a straight line, then we only need 2 temperatures and 2 Ks. Then it's going to be a negative slope, like that. And the slope of that line is going to be negative E sub A over R. So the value of this line is a negative value. So the magnitude of that line is going to be equal to E sub A divided by R, and we know what R is, so we can solve for E sub A. So all we need is the slope of that line, And we can find out what the activation energy for that reaction is simply by conducting the experiment at 2 different temperatures and determine the K for each one. Yes, 8 point, what, 31 something or other?
The joules one?
Yeah. And it should be in useful information.
R is equal to 8.3145 joules per mole Kelvin.
Yeah. Now, actually, there's another useful equation.
Yeah, you got K2, K1, T2, T1.
Yeah,
Which I'm guessing is 2 equations.
it's a combination of the 2 equations. Either one is useful. And then also on that right-hand side, I've got the equations, the rate law equations for the different order reactions. So all your information is right there. Okay. A final word on different types of catalysts. We discussed a heterogeneous catalyst before with the catalytic converter in your car. All that's required for a heterogeneous catalyst is for the catalyst to be in a different phase than the reactants.
Solid gas.
Right, so you've got a solid catalyst and gaseous reactants in your automobile exhaust. You can also have homogeneous catalysts, where the catalyst is in the same phase as your reactants. And the example I gave you last week was the decomposition of hydrogen peroxide using Ki. Did I do that one?
You mentioned it, probably.
Yeah.
Seems like you mentioned that.
Yields this plus that. So that will happen, you know, over time, and it'll happen faster if you heat it up. But if you put some iodine in there, it will happen very fast. And I had a student in a class I was teaching at Logan, whose wife was pregnant, and they found out from ultrasound what the sex was. So they were doing a reveal party. And he got, on the internet, you can buy 30% hydrogen peroxide. It's 10 times as strong as what you get on your cabinet shelf, medicine cabinet. And then he took potassium iodide, which supplies the iodine ion, and a little dish soap to make it foamy, and the food coloring, you know, blue for the boy, red for the girl, and it would come out looking pink. And then he put those in there together, and then when they got ready to reveal, he just dumped this into the bottle, and he went in the color of the child. And he videotaped it. But iodine then offers an alternate pathway for the reaction. It reduces the energy required, the activation energy for that reaction. Consequently, it goes faster. Okay, so I think that was all there was.
So it doesn't look like there are any problems on this practice test with the Rainiest Equation.
Oh, they're not. That's possible that they're not. Let me confirm that they're not. They don't mysteriously show up on the exam. So if you were given, let's see. With this as your model, and you know from this equation that's given in your useful information, how to interpret that graph. If you're given the equation of that line, say it's, I don't know, if this is y and that's x, say we have y equals, I don't know, minus 3 times 10 to the minus third x, and then let's keep it positive, plus, I don't know, 30. Let's keep it simpler. Then how would you find out what E sub A is from that equation? Well, you know the slope is this, right? There's your slope. Set that equal to this. Plug in the value that you know is constant for R and solve for E sub A. Right? So if we said minus E sub A, and what's R? 8.3?
145.
145. Okay. So that one is equal to this slope, which is minus 3 times 10 to the minus third. Okay. So then we say minus E sub A equals 8.3145 times minus 3 times 10 to the minus third. And the minuses go away. And then E sub A is this times that. That's your activation energy, which should be joules per mole. So that's how you would use this to calculate your E sub A value, activation energy for that reaction, using this straight line expression for the Arrhenius equation. And then, of course, let's see. Trying to think. Oh, once you know what E sub A is, you can plug it in here, plug that in there, whatever temperature you want, and find out what your K is at that temperature. Since it's a straight line effect, then you pick the temperature. It doesn't have to be one that's determined by your experiment. Once you found out what this is, then you can just pick the temperature and calculate what K is. Because you know what A is as well, here. So you would plug 30 in there, and you plug your E sub A in there, or whatever temperature you pick, you find out what K is. Okay? So once you've got that equation, you can hop on your horse and ride off in every direction.
What happens with that little e in the first equation?
What happened to this one?
That's just a subscript, right?
That becomes the base of your log.
Right, that's how you get.
Oh, that's a value?
Yeah.
Little e is a value?
If we have, if we take the log of both sides, then the log of K equals the log of A plus the natural log of E to the minus E sub A over RT. Remember, log of E to the base E is just this value right here. Right? So then you get log of A minus E sub A over RT is equal to the log of K. So log of K is still here. And then we get minus E sub A over RT plus the log of A. I'm just putting them in different order. Right? Putting this one over here, that one over there. Okay? And then if we factor out here, minus E sub A over R times 1 over T, because it's in the denominator. Okay. So there's your derivation of this equation. And the reason we wanted to put them in a different order is because we know A is a constant. We know K is a constant. or actually K varies with T. So this is approximating in a linear form. So this becomes Y, this becomes X, this becomes our slope, and this becomes our y-intercept. That's the reason it's written that way.
So with this information, we should be able to do all of these problems.
Should. I would encourage you to practice. Because, I mean, once you get smacked in the face with a word problem.
Yeah, well, go ahead and make you number 19 or number 20, one of those.
All right.
That would definitely be beneficial, I think.
One second. 19. Okay. This is one where we're using the modified equation. Okay, what do I mean by that? Let me erase this and this one. That's just derivation. And the modified of the modified is this one's going to be log of K2 over K1 equals E sub A. I think that's right. Be sure I didn't make a typo. Yes, that's right. E sub A over R, and then 1 over T sub 1 minus 1 over T sub 2. Right. And the log A drops out because it's a constant value, and when we produce this equation, the A's subtracted themselves out. They've just gone. That's why this is somewhat more useful if you know 2 Ks at 2 different temperatures. And the reason the negative went out is because instead of subtracting 1 from 2, we subtract 2 from 1. And that takes that minus out. It's a bit of mathematical legerdemain. Okay, so 19 then is, okay, for the second order reaction, NO plus O3 yields NO2 plus O2. I assume that's nitric oxide depleting the ozone layer. The rate constant has been measured to be 1.08 times 10 to the 7th at 298 K. And the activation energy has been measured to be 11.4 kilojoules per mole over the temperature range 195 to 304. That means we're within the acceptable temperature range change to be sure that our activation energy calculation is valid. So what's the rate constant at 233? Okay, what do we know? All right. So temperature 1 and temperature 2. So the temperature 2 we're going to keep as the high temperature, I believe. Yeah. So temperature 2 is going to be 300 and
4.
am I looking at the right
I
one?
thought it was 233, 298. The initial
Yes.
298.
Oh, I'm looking at the wrong one. I'm sorry. 298 is the high one. And 233 That's the one we don't know. This is the one we know.
So T2 is always going to be a bigger number, even though that's the one.
It just definitely has to correlate. This 2 goes with that K, and this 1 goes with that K.
That's the one.
Yes.
Okay.
So the K for 1, which is the one we don't know, and the K for 2 is 1.08 times 10 to the 10 to the 7. Okay. So that's what was given. Now if we do the log of K2 is 1.08 times 10 to the 7 divided by K1. That's our unknown. And we're given the activation energy. I did write that down. Activation energy is given as 11.4 kilojoules per mole. Okay, here's where you could mess up. Kilojoules, but this is in terms of joules. Right? So this has to be 11,400 joules per mole. You got to change it to joules. All your units have to match.
Right, not the same activation energy because it's within the range of 195, 3, or 4, or inside.
Yes. Right. If we get outside that range, then there's probably some deviation from that value.
And, okay, so we're changing it to joules because of the R.
Because of the R, yes.
So it makes it 11,400.
400. And then R is 8.3145. I'm not putting the units in, but probably want to do that. And then T1 is 233. And T2 is 298. Okay. Now all you have to do is solve for K1. So how do we do that? Well, yeah, this would be the first trick. That's simple. Your calculator will do that for you. This one, since that's an unknown, you got to be able to get that K1 out of there so you can solve for it.
So you got to do log of the first one over log of K1, and then multiply both sides by log of K1.
No, you have to convert this log to its equivalent. Log 1.08 times 10 to the 7th, 10 to the 7th, minus log K1.
Why is it?
When you divide A divided by B, when you take the log of A divided by B, it's equal to the log of A minus the log of B. It's minus the denominator.
So it's kind of like the inverse of multiplication, where it would be addition.
Mm-hmm. Yeah, if these were multiplied together, it'd be log of A plus log of B, but since it's divided, it's log of this minus log of that.
It's going to take some mental gymnastics to remember. Because it's very natural to just want to do, okay, you do log of the top and then log of the bottom and divide.
Yeah, can't do that, not logs. And then you reduce this one to whatever it is, like take the inverse of that and subtract the inverse of that, multiply it by this, divide by that, then you get a number over here. Let me see, did I do that already? Yes. So if you do all that, this reduces to 1.283, and this becomes 16.195. Right? So how do we resolve this? Well, you take this one, subtract that one, bring it over here. So that's this one.
I'm trying to.
Equals log of K1. Right? So this one goes over here, becomes a negative. This one goes over here, becomes a positive. Okay?
So log of K is equal to that.
That, right.
And you do log of that, right?
Right. This is log log of K1. Oh, then this becomes 14.9, which is that minus that. Then to find out, this is where you do the anti-log. So the anti-natural log then would be e to the 14.9 equals K1.
I got 1.28, yay, I'm back there, I wanted to make sure. So I'm sorry, you're going way too fast for me.
Okay, you got this part.
Yeah, I wanted to make sure, I haven't had math forever, but like I have to
Okay.
make sure I can use a screen calculator.
And then
I'm sorry, it sounds terrible, but it's true.
so you got that. Now you need to do the natural log of this number to get that number.
Okay, so, the natural log of 1.08 times 100. So
Mhm.
how do you type that in your calculator correctly?
I don't know about yours. Mine's a reverse Polish. So I do it one way and you probably do it another. I just type in the number and hit natural log.
Okay.
You might have to put in natural log and then type in the number and say equals in an algebraic calculator.
Well,
Yeah, I can't see it.
what,
So punch the natural log button, then enter this value, 1.08 times 10 to the 7th.
how do you put in 10 to the 7th correctly? I don't even know that.
There should be an exponent key in there.
So what
No, it'll be like 10 to something. It's not that one. It's more like, is it double E? Try that one.
second,
Yeah, and then 7. And close parentheses. Hit enter. Yeah, that's it.
16.195.
195. Remember what you did.
So there should be like it's not just gonna be like E something, it's gonna be, like there's gonna be a button on the calculator.
Oh yeah, for the LN key,
Should be right above it, right?
yes, should be right above it, e to the x.
EDX.
Mm-hmm.
For what's e to the x again?
For this one, when you want to resolve this e to the x, will be the key that's just above your LN key.
Okay, so you guys got way ahead, so I'm back over here.
Oh, this one?
I solved for that log and got 16.195.
Okay. So we're still, this one minus that one
the
equals that one.
log of K1
Mm-hmm.
equals 1.28, which I got.
Right. So now we rearrange the equation to put K1 on its side of the equation and everybody else on the other side. So I just took, since this is negative, I just put it over here and makes it positive.
Right.
Then I put this one over here and makes it negative.
So we took.
So that's what this is right here.
So we got 16.195 minus 1.283 equals a positive log of K1.
Yes. And then I just subtracted these two and I got that value.
14.9. So the log of K1 equals 14.9.
Mm-hmm.
So now how do you?
Okay, then you have to consider, what does log mean? It means this is base E. So E to this power equals that. That's what logs mean. The base to that power equals this value. That's why I wrote it this way. E to that power equals this. And that's how you put it in your calculator.
Okay. So you put it in your calculator like that. And what's the E value?
Well, you know where you find the key on your calculator for ln, for the natural log?
Okay, so just for a second function, and then what, type in 14.
And 14.9, yeah, and say equals.
14.9, and then say enter.
Uh-huh.
I got a big number. So let me count that.
What'd you get?
2, 3, 4, 5, 6. So 2.95 times 10 to the 6.
Close enough. For a multiple choice test.
No, I guess yours is 2.99 on the paper.
Yeah. Let me see if I did that right. Get my calculator. I may have calculated wrong. Let's see, 14.9, and then I'm going to do there. I got 2.96.
Well, yeah, 2.96 if you round up.
So this is wrong. It should be 2.96 times 10 to the 6. Make that correction for the next class.
Oh my goodness.
What you know what I may have done?
The method is the same.
What I took was, I left the calculation in my calculator 16.195 minus 1.283 with all of its decimals. And then when I did the anti-log, it gave me 299 instead of 296. Okay?
Wait, so you call that, this E to the X button, that's the anti-log? That's what you call it?
Yes.
Not quite as simple as summing to -1.
No, that would be an error. You're not taking the inverse of the log. You just want to walk the equation backwards. You want to resolve it for what a log actually mean. Base to that power equals this number. That's what an anti-log does.
And so, just going back to when you were explaining the logs, the natural log is an irrational number. That's why we can solve it, why it resolves.
Yeah, I mean, it's a real number.
Just like,
It's just, it's like pi, yeah.
sorry to be stuck at 16 years old in algebra 2, but
Okay.
that's where I left off.
So we ready to talk about the lab?
Yeah. Definitely not looking forward to this evening.
Let's see. That recording is probably going to shut off because I only gave it an hour and a half.
Is that recording going to like be online, or is it like a live stream install?
No, it's recording. I just haven't figured out how to put it on Blackboard yet. I will. If I can't do it, I'll call Dave Ayersman and he'll tell me how to do it.
So this is just pertinent to Coach Lab, right?
It's still recording. I'll just let it go.
This is just pertinent information for Coach Lab, right?
Yes.
Not during the lab or something.
Let me pack this stuff away before I get too confused. There. So this here, this that goes out of the way, and then lab.
So are we going to need more than one? Big ones?
You shouldn't.
It gives time estimates in the addendum from instructors. let's see here. The estimates. Let's start the pages. Activity 120, activity 220, and activity 210.
Yeah, and you don't have to do both colors.
No.
Since we've got a small group, we're just going to pick one color, blue or red, it doesn't matter, and just run that. Then you'll have a different. Well, what would you do there? You have a mess. Yeah, that would really complicate things. Because then you'd have 3 reactants rather than the red color and the bleach. You'd have the red, the blue, and the bleach. Okay, so let's see the pre-lab question. Where is it? Where is it? Pre-lab. Here we go. So this gives you practice in determining the molarity of your bleach. Because when you dilute your bleach in the reaction mixture, you can tell what the concentration is of that reactant, right? So it's using 5% sodium hypochlorite. Ours is 6%, so you just have to substitute the 6 in there and you can determine concentration. The density of this bleach is 1.08 grams per mil. For 6%, you would need a different density, right? And I believe the density for 6% is just 1.09 grams per mil, just for future reference. Calculate the molarity. Okay, so this is actually just a dimensional analysis problem. Let's see. Okay. What we want to do is get this 5% in a useful form, because percent is a dimensionless number. It's parts per 100. So you have to know what parts on top and what parts below, right? And what we're saying is that it is mass per volume. So that means 5, and actually it's we can give as many decimals as we want. So many grams per, wait a minute, so many grams per 100 milliliters. Okay. And this is sodium hypochlorite, so many grams per 100 mils.
Hypo?
Yeah, sodium hypochlorite. Remember polyatomic ions? Right. There's chlorate, there's chloride, there's hypochlorite, and there's perchlorate. Right. So this is sodium hypochlorite. Bleach. So we need to, let's see, grams per liter. Ah, wait a minute. They're saying that this is mass. So it's 5 grams per 100 grams. bleach. Okay. So now what we want to do is convert that to grams per liter. Right. So this is grams of bleach. That's the problem with percent. You got to know grams is not always grams. It's grams of sodium hypochlorite, but this is grams of bleach. So our density says that we have so many grams of bleach per milliliter of bleach. Right. So this is 1.08